So in today's lecture, I'm going to do ordinary differential equation lecture, exact differential equation. Okay, this lecture is about exact differential equation, the definition and the theorem. So let me start with the exact differential equation, the definition for the exact equation. The differential equation of the form m of x comma y plus n of x comma y into y dash is equal to 0 is said to be exact when there exists a function f of x comma y such that dou f by dou x is equal to m and dou f by dou y is equal to n. When if these conditions are satisfied, then we can say it is exact differential equation. Okay. Next, this can be also written in one more form, that is, if m and n are the functions of x and y, then the equation m dx plus n dy is equal to 0 is called exact when there exists a function f of x comma y of x and y such that dou f by dou x dx into dx plus dou f by dou y into dy is equal to m dx plus n dy. That means dou f by dou x is equal to m and dou f by dou y is equal to n dy. If this condition satisfies, then we can say that the given differential equation is exact differential equation. Okay, next let us go to one example. Let me give you all one example. The differential equation y square dx plus 2xy dy is equal to 0 is an exact differential equation because there exists a function f of x comma y is equal to xy the whole square such that dou f by dou x is equal to y square and dou f by dou y is equal to 2xy. Okay. So if it is with respect to x, you will get y square. If it is with respect to y, you will get 2xy, right? Now, on the next page, so we can write d of xy into y square, the derivative of this. We are finding the derivative of this. So, derivative of this will be equal to y square dx plus 2xy dy. Okay? So, now, what is this equal to 0? So this gives you what first, now this is equal to 0. Now, so if the derivative of any function, if it is equal to 0, so the function should be constant. So we have to write the function to be a constant. So that's why I've written this constant. X into y the whole square is equal to c. This is constant. And therefore, this is equal to what? F of x comma y is equal to c. And that is the required solution for the given differential equation. Okay. Next is the note. An exact differential equation can be derived from its general solution directly by differentiating without any subsequent multiplication, elimination, etc. Okay, this is just a note which you all have to take. Next is theorem part. It is, suppose that the equation m of x comma y plus n of x comma y into y dash is equal to 0 is exact in a rectangle R and f is a real valued function such that dou f by dou x is equal to m, dou f by dou y is equal to n in R. R is what? A region. So now this is the continuation part. Okay. Prove that every differentiable function phi defined implicitly by a relation f of x comma y is equal to c, where c is a constant over here, is a solution of the differential equation and whose graph lies in R. So proof starts like this. We know that the first order general differential equation is of the form y dash is equal to f of x comma y, right? Now, in this differential equation is in the form of y dash is equal to minus m of x comma y upon n of x comma y. Next, I'll continue on the next page. So, therefore, m of x comma y, what is m of x comma y is equal to, m of x comma y plus n of x comma y into y dash is equal to 0. Take it as 1. Therefore, m of x comma y into dx plus n of x comma y dy is equal to 0, where m and n are real valued functions of x and y on some rectangle R. So let me explain you all this part. See this diagram over here. I will do it properly on the next page. Let's start with it. So this is done like what? And there will be one more line over here like this, and then there will be one more thing. Okay, now suppose this is your A part, okay, this, and then there is, take one more, this is your B. This is your D, and suppose this is your C and this is your D. So what is going to happen? This part which I have taken, now this is my R, region R, okay? And this is x-axis, this is y-axis. So here this x lies between A and B, and here the y will lie between C and D. And this is my region. This is nothing but a region for you all to understand, okay, this part properly. Because this is the rectangle R. For some, rectangle R meaning this. Okay. Now let me do the differential equation 1. Now this one is said to be exact in R if there exists a function f such that dou f by dou x is equal to m and dou f by dou y is equal to n in R, okay? And take this as 2. Here f is a function, satisfy equation 2, then equation 1 becomes dou f by dou x is equal to x comma f of x comma y plus dou f of x comma y upon dou x into y dash is equal to 0, okay? Just see this and you all can take down this. And then after writing this, if phi is a solution on some interval I meaning if this phi is a solution. Suppose somewhere in between, if this phi is a solution, phi of x, okay? So in some rectangle, the interval I, okay, that is some interval I. So then dou f of x comma phi of x upon dou x plus dou f of x comma phi of y into upon dou y into phi dash of x is equal to 0, and take this as 3 for all x in I. For all x in I it is, okay. Now if phi of x is equal to f of x comma phi of x, then equation 3 can be written as, I made a spelling mistake over here, can be written as phi dash of x is equal to 0. Now this implies that f of x comma phi of x is equal to c, where c is constant. Thus the solution phi must be a function which is given. So multiplicity by the relation like f of x comma y is equal to c for all x in I, and derivative satisfies equation 3. Hence phi of x is the solution of the given differential equation, hence proved. So okay, this part write it on the next line, okay, and then this, hence proved. So in the next lecture I will be proving one problem on exact differential equation, that is that is this one, y dash is equal to 3x square minus 2xy upon x square minus 2y. In the next lecture I will be doing this. If you all have not understood any of the concept of today's lecture, you all can comment below, and thanks for watching.